Welcome to Chapter 2 of the Nova Sigma Field Propulsion dossier. In this segment, we move beyond the foundational physics and field geometry of Chapter 1 to focus on the real-time control, stability, and failure containment that make this advanced propulsion system possible. Here, we'll see how the system is governed by rigorous mathematics, ensuring it remains stable and reliable in any environment. We'll explore the control architecture, the logic behind stability enforcement, and the robust strategies that prevent catastrophic failures. This chapter is all about how the Nova Sigma system achieves precise maneuvering and safety through advanced engineering, not just theoretical concepts. Let's begin our journey into the heart of control theory and system resilience. At the core of Chapter 2 is the formalization of control mathematics for the Nova Sigma field propulsion system. Unlike traditional propulsion, this system is managed as a coupled tensor, field optimization problem, operating under strict continuity and eigenvalue constraints. The control problem isn't just about pushing or pulling, it's about shaping fields and inertia in real time. This approach allows the system to adapt instantly to changing conditions, ensuring smooth transitions and minimizing internal stress. The mathematics behind this control logic is what enables the Nova Sigma to perform extreme maneuvers while maintaining stability and safety, setting it apart from conventional designs. The lambda matrix is the brain of the Nova Sigma control system. It's a hierarchical closed-loop controller that coordinates four critical domains: inertial tensor control, sigma core, energetic gradient control, gamma engine, boundary continuity control, Ω-Sheath, and supervisory stability and fault logic, lambda supervisor. Each domain operates independently, yet all are phase-locked to a global coherence clock. This architecture ensures that every subsystem works in harmony, allowing for distributed control authority and instantaneous reconfiguration. The lambda matrix is what makes real-time, stable operation possible, even during the most demanding maneuvers. Fully describe the system at any moment, the Nova Sigma uses a comprehensive state vector. This vector includes the inertial tensor field, energetic gradient vector, translational and angular velocities, and environmental boundary parameters. By capturing all these elements, the control system can respond dynamically to both internal and external changes. This holistic approach ensures that every aspect of the craft's behavior is accounted for, from how it accelerates to how it interacts with its environment. The state vector is the foundation for all subsequent control actions and stability checks. Lambda matrix enforces a unified control law, aiming to minimize deviations in both the energetic gradient and the inertial tensor from their commanded values. This is achieved through a mathematical objective that integrates these differences over time, subject to constraints that guarantee smooth transitions and bounded accelerations. By adhering to these strict conditions, the system avoids sudden shocks or stresses, ensuring both performance and safety. This unified approach is what allows the Nova Sigma to maintain precise control, even in rapidly changing or extreme environments. Stability is a cornerstone of the Nova Sigma system. The control logic uses a linearized stability operator, where small disturbances are analyzed through the system's Jacobian matrix. The key condition is that all eigenvalues must have negative real parts, ensuring that any perturbation naturally decays over time. This mathematical rigor guarantees that the system won't spiral out of control, even when subjected to unexpected forces or changes. By enforcing these eigenvalue criteria, the Nova Sigma achieves asymptotic stability, a hallmark of advanced aerospace engineering. Further safeguard against instability, the system actively enforces a stability envelope. This involves constraining the curvature of the energetic gradient, preventing the formation of field shocks, tensor tearing, or runaway oscillations. The envelope is environment-dependent but always internally bounded, adapting to conditions without compromising safety. This proactive enforcement is what keeps the system operating smoothly, regardless of whether it's flying through air, vacuum, liquid, or plasma. It's a dynamic shield against instability. Unique feature of the Nova Sigma is its ability to decouple translation and rotation. The lambda matrix ensures that changes in translational velocity do not affect rotation, and vice versa. This eliminates issues like centrifugal coupling or gyroscopic drift, which can plague traditional systems. By maintaining this strict separation, the craft achieves perfect control authority, allowing for maneuvers like spinning without drifting or drifting without spinning. This decoupling is essential for precision operation and advanced flight profiles. The Nova Sigma system is designed to operate identically in any environment, thanks to its environmental adaptation logic. Environmental parameters like density, permittivity, permeability, temperature, and pressure only affect the boundary response, never the core control laws. This means the craft behaves the same whether it's in the atmosphere, vacuum, liquid, or plasma. Such adaptability is crucial for missions that span multiple environments, ensuring consistent performance and safety throughout. One possible failure mode is gradient saturation, where the energetic gradient approaches its maximum limit. When this happens, the system responds by flattening the gradient, normalizing inertia, and automatically decelerating. These corrective actions are designed to prevent the system from exceeding safe operational limits, ensuring that even under stress, the craft remains under control. This built-in response is a key part of the system's fault tolerance. Another failure scenario involves tensor anisotropy overload, where the difference in the inertial tensor exceeds safe thresholds. The system counters this by clipping eigenvalues, redistributing loads, and transitioning to a symmetric inertia mode. These measures prevent structural stress and maintain stability, even when the system is pushed to its limits. By localizing and correcting these overloads, the Nova Sigma avoids catastrophic failure. Boundary discontinuity is a failure mode where the field's boundary conditions are violated. The system responds by reinforcing the Ω-Sheath, smoothing the field, and entering an emergency hover or drift stabilization mode. This ensures that any discontinuity is contained and corrected before it can propagate, maintaining the integrity of the craft's operation. Such robust boundary management is vital for safe operation in unpredictable environments. Defining feature of the Nova Sigma system is its fault containment strategy. All failures are strictly contained within their originating layer, preventing them from spreading across subsystems. This architecture ensures graceful degradation rather than catastrophic loss, so even if one part of the system fails, the rest continues to operate safely. This layered containment is a hallmark of advanced engineering, providing resilience and reliability in the face of unexpected challenges. Visualize these complex systems. Chapter 2 introduces a series of 4K technical plates. Each plate is a photorealistic engineering diagram, meticulously annotated with mathematical overlays and subsystem logic. These plates are not just illustrations, they are engineering artifacts, directly corresponding to the mathematical framework of the Nova Sigma system. They serve as both validation tools and communication aids for engineers, researchers, and decision-makers. Plate 2A presents the Lambda Matrix Master Control System in full detail. At the center is the Lambda Supervisor core, surrounded by 4 symmetrically arranged subsystems: Sigma Core, Gamma Engine, Ω-Sheath, and Ψ-Diagnostics. Bidirectional vector arrows illustrate the closed-loop feedback that keeps all modules synchronized. Prominent mathematical overlays define the system's state and control objectives, while subsystem labels highlight key functions like phase locking and eigenvalue monitoring. The dark aerospace blueprint background and ultrasharp topography make this plate both functional and visually striking. Plate 2B zooms in on the Sigma core, the heart of inertial tensor control. The diagram reveals a tensoractive internal lattice, visualized as a 3x3 field matrix. Directional arrows indicate regions of inertia compression and expansion, while color-mapped zones show intensity variations. Mathematical overlays detail the tensor's structure and dynamic constraints, illustrating how the system reshapes inertia in real time. This plate explains how the craft achieves rapid acceleration and sharp turns without structural stress. Plate 2C illustrates the Gamma Engine, responsible for energetic gradient control. The diagram features field gradient lines flowing asymmetrically around the craft, with high-density zones representing thrust vectors and low-density zones indicating hover states. Mathematical overlays define the effective acceleration law and curvature constraints, showing how the system produces thrust without reaction mass. This plate highlights the core innovation of field-propelled motion, enabling identical performance in any environment. Plate 2D focuses on the Ω-Sheath, the boundary field that isolates the craft from environmental effects. The diagram shows a stability envelope surrounding the craft, with the external environment faded out for clarity. Mathematical overlays specify environmental parameters and boundary conditions, emphasizing that only the sheath responds to changes in air, water, or plasma. This plate demonstrates how the system achieves zero drag and stable hover, regardless of the surrounding medium. Plate 2E demonstrates the system's approach to failure containment and fault isolation. The layered cross-section of the craft shows fault points originating within individual subsystems, with no cross-layer propagation. Mathematical safety conditions are overlaid, confirming that the system enforces local degradation and automatic fallback modes. This plate visually reinforces the concept of graceful degradation, ensuring that no single failure can compromise the entire craft. Plate 2F proves the system's ability to decouple all 6 degrees of freedom. The diagram places the craft at the center, with separate vector sets for translation x, y, z, and rotation, roll, pitch, yaw. No vectors intersect, illustrating perfect independence. Mathematical overlays provide the formal proof, while annotations highlight the absence of gyroscopic coupling or centrifugal drift. This plate is a testament to the system's precision and control authority. Together, these plates provide a comprehensive validation of the Nova Sigma control, stability, and failure containment architecture. Each diagram is grounded in mathematical rigor and engineering logic, serving as both a blueprint for implementation and a benchmark for system performance. The visual language is consistent across all plates, reinforcing the system's coherence and reliability. This level of documentation is essential for high-level technical reviews and defense briefings. Operational significance of the lambda matrix control system cannot be overstated. By distributing control authority and maintaining phase-lock feedback, the system prevents unstable amplification and enables instantaneous reconfiguration. This means the craft can adapt to new commands or environmental changes without hesitation, maintaining coherence even during extreme maneuvers. Such agility is a direct result of the advanced control logic visualized in Plate 2A. Sigma Core's ability to reshape inertia on demand is what enables the Nova Sigma to perform non-Newtonian maneuvers. By dynamically adjusting the eigenvalues of the inertial tensor, the craft can reduce resistance along acceleration vectors and increase it orthogonally for stability. This eliminates the risk of inertial shock to both the structure and occupants, making high-speed turns and rapid acceleration safe and comfortable. Gamma Engine's energetic gradient control is the heart of field-propelled motion. By manipulating field gradients rather than relying on reaction mass, the system achieves thrust and acceleration in any environment. This innovation allows for identical performance whether in atmosphere, vacuum, or plasma, and eliminates the limitations of traditional propulsion methods. The ability to hover, translate, and rotate with such precision is a direct outcome of this advanced engineering. The Ω-Sheath ensures that the craft remains unaffected by external conditions. Whether flying through dense atmosphere, underwater, or in the vacuum of space, the stability envelope adapts to maintain optimal performance. This decoupling is what allows the Nova Sigma to operate seamlessly across diverse environments, providing unmatched versatility and reliability for a wide range of missions. Fault tolerance is built into every layer of the Nova Sigma system. By containing failures locally and enforcing strict safety conditions, the system ensures that no single fault can compromise the entire operation. Automatic fallback modes, such as emergency hover, activate without pilot input, providing an additional layer of safety. This approach guarantees that the system degrades gracefully, maintaining control and stability even under duress. The interaction between subsystems is governed by a network of bidirectional feedback paths. Each subsystem, whether it's the Sigma Core, Gamma Engine, Ω-Sheath, or Ψ-Diagnostics, operates independently but remains synchronized through the lambda supervisor. This architecture allows for distributed decision-making and rapid adaptation, ensuring that the system remains robust and responsive at all times. Every technical plate in Chapter 2 features mathematical overlays that define the system's operational logic. These equations are not just decorative, they encode the constraints and objectives that the control system must satisfy. From state vectors to optimization objectives and safety thresholds, these overlays provide a transparent link between theory and practice, ensuring that every aspect of the system is both verifiable and reproducible. The Ψ-Diagnostics subsystem plays a crucial role in feedback, sensing, and fault isolation. By continuously monitoring system health and performance, it enables early detection of anomalies and rapid initiation of corrective actions. This proactive approach to diagnostics is essential for maintaining the high reliability and safety standards required by advanced field propulsion systems. Synchronization across all subsystems is achieved through a phase-lock clock, ensuring that every module operates in perfect harmony. This synchronization is vital for maintaining global coherence, especially during rapid maneuvers or environmental transitions. The phase-lock clock is a subtle but essential component of the overall control architecture. The Eigenvalue Monitor and Tensor Normalizer are specialized subsystems that ensure the system remains within safe operational bounds. The Eigenvalue Monitor tracks stability criteria in real time, while the Tensor Normalizer adjusts inertia to prevent overloads. Together, they form a critical safety net, automatically correcting deviations before they can escalate into failures. The gradient smoother is responsible for maintaining smooth transitions in the energetic field. By preventing abrupt changes or spikes, it protects both the system and its occupants from sudden shocks. This function is especially important during high-speed maneuvers or when transitioning between different operational modes. Visualizing the tensor lattice within the sigma core provides insight into how inertia is dynamically reshaped. The 3x3 matrix structure allows for precise control over mass distribution, enabling the craft to adapt its response to any command. This visualization is key to understanding the advanced capabilities of the Nova Sigma system. Directional mass bias arrows on the sigma core plate illustrate how the system can lighten or anchor mass in specific directions. This capability is essential for achieving rapid acceleration, controlled braking, and stable hovering, all without imposing undue stress on the craft's structure. The ability to compress or expand inertia in real time is a defining feature of the sigma core. By adjusting these parameters, the system can optimize performance for any maneuver, from sharp turns to sudden stops. This dynamic control is what sets the Nova Sigma apart from traditional propulsion systems. On the gamma engine plate, field gradient lines represent the flow of energetic forces around the craft. High-density regions correspond to thrust vectors, while low-density zones indicate areas of neutral or minimal force. This visualization helps explain how the system generates motion without relying on traditional engines or exhaust. Lift and translation gradients are key to the craft's ability to maneuver in 3 dimensions. By precisely controlling these gradients, the Nova Sigma can achieve smooth, controlled flight in any direction, regardless of external conditions. This level of control is essential for advanced aerospace applications. Rotation isolation zones on the gamma engine plate show how the system prevents unwanted rotational coupling. By isolating these zones, the craft can rotate independently of its translational motion, enabling complex maneuvers like spinning in place or executing rapid orientation changes. The Ω-Sheath plate features a shield-like field transparency, visually separating the craft from its environment. This transparency is not just aesthetic, it represents the real boundary that protects the craft from drag, turbulence, and other external forces. The engineering-grade clarity of this visualization underscores the system's advanced protective capabilities. Drag nullification and pressure isolation zones are highlighted on the Ω-Sheath plate. These regions ensure that the craft experiences minimal resistance, even at high speeds or in dense environments. This capability is crucial for efficient, high-performance flight across a range of mission profiles. The plasma deflection boundary is a specialized feature of the Ω-Sheath, allowing the craft to operate safely in high-energy environments. By deflecting plasma and other charged particles, the system maintains stability and protects sensitive components, enabling missions in space or near-energetic phenomena. Color-coded containment zones on the failure containment plate make it easy to identify which subsystem is affected by a fault. This visual clarity aids in rapid diagnosis and response, ensuring that corrective actions are targeted and effective. The use of color coding is a practical tool for both operators and engineers. Automatic symmetry fallback is a built-in safety feature that activates when a fault is detected. By reverting to a symmetric configuration, the system maintains balance and control, even if one part of the craft is compromised. This fallback mode is a key reason why the Nova Sigma can continue operating safely under adverse conditions. In the event of a major fault, the system can automatically enter an emergency hover state. This mode stabilizes the craft and prevents uncontrolled motion, buying time for further diagnostics or intervention. The ability to hover safely, even during a failure, is a testament to the robustness of the Nova Sigma architecture. Chapter 2 has established the Nova Sigma field propulsion system as a fully controlled, mathematically stable and failure-tolerant platform. Through advanced control theory, subsystem interaction, and robust fault containment, the system achieves extreme maneuverability and reliability. The 4K technical plates serve as both engineering evidence and communication tools, bridging the gap between theory and practice. As we move forward, the next logical step is to explore the energy architecture, power scaling, and thermal neutrality that will define Chapter 3. The foundation laid here ensures that the Nova Sigma is ready for the challenges ahead.